to recap, think of database. I'm just taking one data structure, a B plus tree. A representative diagram is here. Essentially, if customer creates a table and has a number of columns, all the data is getting written into these pages of fixed size pages typically. In this case, in Aurora MySQL, we use a 16 kilobyte sized pages. And it is organized in a way such that the data can be retrieved quickly. So if there is a key that is defined, then the tree is accessed accordingly. So that's the crux of this B tree. And this B tree is resident in memory. Obviously, the whole tree, if it is a big database, big table, it cannot be resident in memory. So we use storage. And periodically, this in-memory data is written into the storage so that we can page fault retrieve data that cannot be fit into memory. So that's the idea of the B tree. And the key part about how we modify this B tree. So as an example, we use this protocol, do, redo, undo protocol, where the changes are tracked and used for moving forward and moving backwards. So let's take an example. The old state of a page is given in green color. And say we make a operation to change the data. For example, let's say the first column is modified, incremented a value. Right. So when a customer does that operation, the database goes and modifies that page in memory and then produces a new state. So if the value was 1 here, the value of that column becomes 2 here. And then that operation is recorded in a different storage location called as using a method called as writing a log record. That log record essentially would say this row, this column is modified from this previous value to the current value that the customer has modified. Say the database has to be restarted at that particular point in time, the database file, as I talked about the checkpoint, had the previous state, but the customer has already modified. So what we do is we take the log record from the log file and reapply it. We call it redo, and then get the new state. In some cases, we may have to revert the change. So in which case, we take the new state and then apply the opposite of what has been applied before, and that is called as the undo operation to get the old state. So this is the mechanics of how database moves the state from one to another. So let's take an example. In this case, the time axis is in the y-axis. So let's say a transaction TX1 is in progress, and it's in red in color, and the log records for that transaction is written into the durable storage. Okay. At the time TC, the checkpoint is written. Basically, the database decided that let's flush the pages that have been modified into the database file. In this case, a page was modified because of the red transaction. And while that was happening, a blue transaction was in progress, the transaction 2, and the log records were written into the log. But that change did not make it to the checkpoint, right? Because it was not at over. So on the transaction 3 started, and that the log records, the matching log records were also written in the log file. And while the transaction TX4 was being performed, the system failed. Assume power loss or something that has happened. Okay. At the time of recovery, the database now looks at the log records. So it knows that the transaction 1 was made it to the checkpoint even earlier, but the transaction 2 and transaction 3 are just present only in the log file, but not in the checkpoint. So it would go take those log records and reapply to the previous version of the pages in the checkpoint and produce the blue pages and the green pages. It might be in memory, or it can also be written to the checkpoint. But essentially, the database goes back to the consistent state. And then it knows that the transaction TX4 has not committed. So it basically truncates that. So this is how the previously explained protocol has been applied in practice. So if you look at the database operations, we have, in terms of the number of IO that is required, for every change, that is made, we need to write logs, and it depends on the size of the transaction, the schema, and all of that. But definitely, we need to write some logs, and typically those are small in size. Right? In terms of writing the checkpoint, there is a problem where if you try to write a 16 kilobyte worth of data into a durable storage within a particular location, say in the database file, and if the underlying storage does not support atomic writes of the same size of, say, 16 kilobytes as described here, then there is a possibility if the power fails at the inopportune time, the data that is written may not be complete. So that we call a torn write. So to avoid this, typically the databases write in two places. They first write the 16 kilobytes in a different scratch space, and then they try to write within the checkpoint. So if the power failure happens, it becomes easier for the database to go retrieve the correct version from the scratch space. So for writing 16 kilobytes worth of data, we end up writing 32 kilobytes worth of data. So you can imagine if the customer has modified a single column, say a byte, there is a log record that is written. Usually it's few tens of bytes or hundreds of bytes, but then it ends up writing 32 kilobytes worth of data. So IO is very important to focus on to scale the database. So now let's look at, given this context, how we thought about building Aurora for cloud native architecture. So the architecture of the traditional database architecture looked like this. There is a compute node which processed the SQL statements. It handled transactions. In terms of caching, we call it also buffer pool. You maintain the data in memory. And then you have a logging subsystem that we talked about. Whenever there is a modification of changes, you need to write it to a durable storage. So both the logs and the database pages were returned to the attached storage. So this has been the architecture for several years. Right? And because we knew that IO is a bottleneck, what typically customers and the vendors would do is to increase the bandwidth of the IO, put better hardware, better SAN, better throughput, and so forth. That has been the technique. What we did in Aurora is slightly different. We said, let's look at what is the most critical part in terms of the durability. The log is the most important part because that's what customer initiated as a modification to the database. Let's assume that a log can be used to recreate the database. So the log is the database. So let's assume that from time 0, we have captured all the logs. Okay. So with all the logs, we can recreate any version of the page at any given point in time. Right? So for example, if we want to recreate a red page at T5, then you need to go take the T1 and T5, the log records in T1 and T5, and produce a red page. So log stream can be used to produce the correct version of the page as needed. The question is, if we always rely on the log stream to read the pages, it's not practical. It's just too slow, right? The database could be running for years. So how do we do that? We have to do periodic checkpoints. Now you might ask, okay, this is what database used to do before. So what is novel here, right? Because the database instance is burdened with the checkpointing task. It has to flush the page. It has to deal with the torn writes and so forth. So what we did in Aurora is we offloaded that heavy task to a distributed storage fleet. So essentially the logs are written to the distributed storage, and the distributed storage would do the checkpointing on behalf of the database instance. So essentially we were able to do a massive parallel processing that is done continuously, asynchronously, without waiting for the database engine. So the database engine writes only small amount of IO to the network, while the distributed storage will do local IO doing the checkpointing. Right. That is the first idea. Log is the database. The second idea is to separate compute and storage. So if you look at the lifetime of compute instances, these are essentially the virtual machines that run the database engine. They can fail at any time. And if it fails, you don't lose anything because the data is stored in a distributed storage. It can be replaced. You can turn off the database instance whenever you don't need it. For example, a dev workload, for example, during the daytime, the developer is using it, and then in the evening, it's not being used. So you can turn off the instance and not waste resources. It can be scaled up and down based on the level of the load. So the compute is more ephemeral. Of course, it has caching for performance and so forth, but you can add more, you have more liberty in modifying the capacity of the compute node. In terms of storage, though, it has to be long lived. So what we have done is instead of direct attached storage, put it in the distributed storage by decoupling the compute and the storage, make the compute attached to the distributed storage, and we innovated making multiple compute nodes attached to the same storage volume. And the storage itself is a multi-tenant capability. So we have a multi-tenant, multi-attach storage that the compute nodes can attach to. So we are able to scale independently. In terms of the building blocks that we used, we were lucky to use a lot of building blocks that the other teams in the AWS has built. Like we used the DynamoDB for our metadata for the distributed storage. We use Route 53 for better DNS naming for the endpoints. Use EC2. We don't use any custom hardware for our both storage and for the compute. We use all the EC2 instances that are available for general public. Use S3 for storing the backups, but we built the storage, the log structured storage using NVMe storage on the local device, and we do replication, multi-AZ replication, repair, and so forth. So let's go through how I/O flows in the storage node. The storage node is a component that receives the data from the database instance and then durably persists it. Okay. So in the first step, the database instance sends the log records, the changes that are produced on behalf of the customer. It is sent to the storage node. The storage node adds it to the memory and puts it in a persistent NVMe storage. Immediately it responds it back saying, okay, it has been durably persisted. Once it is durably persisted, it goes and starts sorting it and making sure that it is ready for updating the pages. So we call that task as the update queue. And when we are doing this, we might find out that there may be holes within the sequence of the logs because these machines, hundreds of machines are taking part in durability. Some machine might be down for some reason. Maybe we are updating software or there is network glitch. There could be a number of reasons. So, but when the storage node determines that there is a gap in the sequence, it goes and talks to its peer to get the data that it is missing. Once the sequence is complete, the log sequence is complete, those changes can be applied to the pages to produce the new version of the pages, as I explained. Continuous checkpointing. Another word that we are using here is called as coalescing. Essentially, take the previous version of the page, apply the log records, get the new version of the page. And we store it locally in NVMe. We also send the logs and the pages periodically to S3 so that we can do a point in time restore or a snapshot restore and so forth. So the long-term durability is achieved by putting it to S3. And given that once we put it into S3 and also made sure that all the peers have gotten the log records, we know that that log record is no longer needed after we have materialized it into the new version of the pages. So we continuously garbage collect. And while we do all of these things, we make sure that the corruptions have not entered the system. Right? If you look at all these processes, the most important part, the latency sensitive part, is step 1 and 2. Essentially, the database instance sent the changes to be durably persisted, and then the acknowledgement has to be given. So that is the only thing that is done in a synchronous fashion. Everything else is done in asynchronously. And none of those operations require the CPU and all the other resources that might have taken from the database instance. All of these things are done on the storage node. So the database instance is focusing only on the compute of that is determined by the customer, the query processing and generating the changes and sending it to the storage. Let's look at the how we achieve the scalability. So I already introduced that when we deal with hundreds and thousands of machines, there might be some sort of failures, network failures, machine failures, SSD failures. There can be any failure that can happen that might be independent to each other, right? So typically when you have that type of a problem, the solution is let's replicate it, and the minimum number of copies that we would arrive at is three-way copy. So let's say we have three availability zones, and we can copy each piece of data one per availability zone, and we can tolerate one failure, and we can do a quorum of 2 out of 3, read and write quorum. Right? This is a typical technique. But in that 2 out of 3 quorum technique, what happens if an availability zone goes down? We still have, the whole AZ is down. There are still 2 copies up, one in each one of the availability zone. The database can establish quorum. There's no data loss. But we know that if you're dealing with thousands of nodes, even within a single availability zone, a node can go down for whatever reason, right? So if that happens, then the quorum is lost. Even though you have remaining nodes up, just that one copy can bring the database down, right? So the 2 out of 3 copies is not no longer true. In a particular case, 2 copies might be down, right? The quorum is lost, and you might lose the data. So what we do in Aurora is our design goal was to tolerate AZ plus 1 failure. So instead of making just 3 copies, we are making 6 copies, and we do write quorum of 4 out of 6. So essentially, you can see that we have 2 copies. There are 2 pink copies per availability zone, and so forth. Right. So now what we do is, if the availability is down, AZ is down, there are 4 copies left, and if one more copy is down, we haven't lost the data yet. It's only availability loss. We can rebuild the copy from the remaining 3 copies. In the previous case, there will be only 1 copy left, and you don't know whether that has the latest data, so you really cannot recover. In this particular case, you can recover by copying the data from the remaining 3 copies, and we recover the write availability. And this particular single design philosophy has helped Aurora a lot over the years. It has been close to 7 years. Across several regions, we have had some operational pain in terms of power failure. All of those issues we were able to handle because of this single design choice. Okay, so then the interesting question would be, if you're using hundreds of machines, thousands of machines for spreading the storage, how are they partitioned? So what we do is, first we partition the data into what we call the protection groups. It's a replicated unit that is replicated 6 ways. And the design criteria would be how quickly we can identify the issues and repair. So we really cannot control when the failures would happen, but we can control how fast we can repair. So that's our goal. And we did a lot of experimentation and found that if we create the size of the data to be 10 GB, we can repair it within a minute. And that's the configuration we have gone with. So when you have these type of 6-way copies and so forth, how do we deal with making the metadata changes on what is the right, where is the copy, whether it is healthy or not, and so forth? We use a concept of a quorum set, and we have versioning to it called as epoch. So when in this particular example, there are 6 copies, A to F, and all the nodes are healthy. This is just one protection group that contains replicated 10 GB worth of data. Okay, And if the node F is in suspect state, maybe the ping periodic polling pinging does not work for some reason, the node seems to be not responsive, then we go create a new copy G. But we use both the quorums because we haven't made a decision yet if F is really down and if we are removing it from the replication set. Right? And then once the replication is over, that is G has caught up from the other peers, then we mark that F is no longer needed and we remove it. So just a quick thing here, this particular technique we use even for soft management, heat management. These are not hard failures. So say, for example, a node F is overloaded, then we proactively create a new copy elsewhere and then make sure that the data is written to both F and G while we are rebuilding G. And once G is caught up, we remove F. So that's how we do heat management. And these are not impactful to the customer. So the customer workload continues to happen without any changes. The 4 out of 6 quorum continues to happen while we rebalance the hot nodes. So that's how we do heat management. So the same technique is used for both hard and soft failures. David will take it from here. Dave, can you share your screen or do you want me to drive it?
If you can keep driving the screen, that would be great. Thanks, Murli. So Murli gave you a background into some of the architecture of Aurora, and I'm going to talk through some of the ways that we actually see this working out in benchmarks and in the real world. So here's a look at MySQL doing in a typical setup and the amount of I/O that it has to do. So in this diagram, we have a primary instance in one availability zone and a replica instance in a second availability zone. Two availability zone model is very important for availability. So most customers in a production workload would use a multi-AZ setup. So in the multi-AZ setup, you've got several IOs going on. We've got log IOs. We've got replica in bin log. We have checkpointed data pages. We have some double writes to protect against torn writes in the case of crashes, and some additional files. Now, each instance, so the primary instance actually has to write down to its EBS storage. The EBS storage has to mirror those writes, and we have to do backups coming off of the primary instance into S3 to archive the log files. We also have to replicate writes over to the second instance where they are received, and then, that instance must persist them. So it has to write down to EBS, and that EBS has to mirror. So, what we found in a 30-minute sysbench run, it did 780,000 transactions and did an average of 7.4 IOs per transaction. Okay, so that's what we saw with regular MySQL. Now, Aurora doesn't use EBS, and the replicas are actually readers attached to the same volume, and so they're not actually replicating their data separately. So in this case, we are just writing down the log records. Now, some people think, hey, you've got to write 6 copies of things, so this isn't going to be any faster. But we only have to write the log records. And as Murli talked about with the checkpoints and the double writes for torn pages in Postgres, there's also this thing called full page writes of index pages that cause a lot of bloat in the logging after a checkpoint. All those things were adding up to that IO per transaction. So when we look at Aurora, even though we're doing 6 copies, we're doing 6 copies of a lot less. We don't have to do the S3 backups off the database writer because those are happening continuously from the distributed storage. And the read nodes that receive the change stream only need to apply that change stream in memory to keep their cache accurate, because the actual storage is on these multi-attached volumes that we can go to. So the net result of this 30-minute sysbench run is we actually did 35 times more transactions, 27 million transactions versus 780,000. And we did just 0.95 IOs per transaction. So even with the amplification, we were 7 times less. So far less IO. By the way, Merle mentioned really early, it's an easy thing to miss. He said, the kind of the low bar for Aurora is to be better than open source, cheaper than enterprise. Seems kind of reasonable, right? You want to be better than open source, and you want to be cheaper than somebody like Oracle and SQL Server. So there's a lot of space in there. But the actual high bar we have is to be better than enterprise, right? And to be cheaper than open source. And how are you cheaper than free? Like, how can you be cheaper than free? You can be cheaper than free because you're more efficient with the compute and storage resources. And so this is one way we can actually be cheaper than free is, cheaper than free for software, is that we are more efficient on the IOs and we use less resources. So how does this translate out? This is looking at Aurora MySQL, and we claim that we're up to 5 times faster. There's a lot of work that was done on both the IO side and within the MySQL 5.6 and 5.7 engines to unblock a lot of concurrency layers, sort of peel back the throughput onion, and get better throughput in lock manager and other areas of the code. On read throughput, we're also faster. There's a recache that can use. So you can see this is just with the standard suspension. We get significantly better throughput. Go to the next slide. All right, now this one I want to talk a little more about. This one is looking at a Postgres system, and we talked a little bit about checkpoints and how in a traditional database architecture, your database writer has to be doing checkpoints, which is writing the dirty full pages of cache back to disk, truncating the logs, establishing a new resource point, restart point, things like that. And so we tend to call those checkpoint spikes. And so those are huge spikes in IO as a background writer process goes through and washes the cache and flushes it to disk. And so we can see that here. We compared a Postgres running on EC2. There was just a single AZ, and compared to, that's the blue line, compared to Aurora, which is in 3 AZs with continuous backups, and that's the green line. And the y-axis is the response time. Okay, so the response time on individual queries, and then on the x-axis is just going out in time. And you can see this wild variation in response times for the regular traditional open source database, and that's due to checkpoint spikes. And in Aurora, we just see a fairly steady response time living within a certain range. And that's what getting rid of checkpoints really gets you. And so, you could extend out your checkpoint interval so checkpoints don't run as frequent, and you can make the blue line look a little more like a green line for longer period of time, but eventually you pay the price and you get a big spike sometime, or you make recovery very long. So if you go to the next slide, Merle, and we talk about now recovery and checkpoints. So this slide, the typical trade-off in databases with checkpoints and recovery is the longer you've gone since you checkpointed, the more of a redo log you have built up. And when you want to restart your database, if for some reason it crashes or something like that, you go to the last checkpointed time and you roll your redo log forward. So this is example on the x-axis. We're talking about how much throughput the database was doing at the time of a crash. And on the y-axis, we look at the time to do recovery. Okay, and then the dot size represents the amount of log that was generated that had to be applied. All right, so if we look at the 3 dots on the left, we see that running at a fairly low write rate, this is with community Postgres, a fairly low write rate. When it crashed, we had 3 gigabytes to redo, and it recovered in 19 seconds. Then if we increase the write rate, this is more log since the checkpoint. We have more redo to do. There's more log, and it takes longer to recover. And as the transaction rate goes up and the writes per second goes up, we start bloating our redo log, and recovery takes longer. So again, typically in database world, you would play with tuning your checkpoint intervals to try to balance out the amount of throughput you needed versus the amount of time you were willing to spend on recovery. But if you look all the way out on the right side of the x-axis, we see Aurora. Aurora doesn't have to do any redo on startup. This is Aurora Postgres, doesn't have a redo log to redo. And so in this case, it recovers in 3 seconds while doing significantly greater write traffic than Community Postgres did. And so this is sort of one of the key benefits of the architecture and the distributed checkpoint. So very fast recovery without checkpoint spikes. Okay, next slide. Okay, so we have a bunch of customer success slides here. We're actually going to just blaze through them because I want to spend the time on talking about some other upcoming engineering challenges we have. The point here is that we have a very large and successful business on Aurora at this point. It's sort of been successful beyond our wildest dreams. It remains one of the fastest growing, if not the fastest growing service at AWS. And so there's a lot of collateral on customers, big customers that you know, name brand customers, either traditional enterprises or sort of board in the cloud customers. They've been very successful with Aurora. We have a lot of success with migrating enterprise databases. We have a database migration service that helps with that. And so we bring a lot of workloads over from the likes of Aurora, Oracle and SQL Server. So in the interest of time, Merle, let's page through some of these slides. By the way, I'll just pause briefly. One of our biggest and most successful customers is Amazon.com, which is, you think, we're AWS or part of Amazon, but Amazon.com was an Oracle shop for many years, and we've transitioned all the Oracle is gone, and a lot of it's moved onto Aurora. Some has moved to Dynamo, depending on the work use case, but all of Amazon fulfillment is running on Aurora. So let's just go through these. Let's skip ahead to the what's next slides. So as you can see, we just have a lot of customer success slides. For this audience, I just want to talk about some more of the technical things that we're looking to solve going forward. I'm the one that told Merle to put those customer success things in the deck, so that's all my fault. Okay, so what are some hard problems and things we need to look at going forward? We've learned over the years that customers really care about community open source compatibility. And so Aurora Postgres is really 100% compatible with Postgres. Like anything you can do in Postgres, you can do in Aurora Postgres. So this has been very important to our customers and has really been a huge uplift for the Aurora business. So how do you build the one challenge that we balance on an ongoing basis is how do we stay current with community innovations? How do we contribute back to the community, but do our own innovations as well? So we have worked very intentionally to architect our system in a way that allows us to not just create an initial version that sits there, but to stay current with every Postgres major and minor release. So next slide. So the biggest challenge we have at AWS is scale. That's always the hardest thing. That's always the hardest thing at AWS is scale. And so we can look at scale on 3 different levels. We have challenges of solving scale within the database. So right now, Aurora supports a 128 terabyte database. That's not big enough for some customers. We have customers running on sort of 13 node Aurora clusters, pushing well over 1 million read-write transactions per second, not enough throughput, right? Serving thousands of connections at a time, not enough concurrency, right? We got more CPUs, more memory, more storage, more parallelism. So there's all this, continue to scale the system stuff that's fairly typical. We also have to scale down because part of the promise of the cloud is sort of pay per use, right? And some customers have spiky workloads. So we've recently launched a really great thing in our Aurora Serverless V2 offering, which does sort of online scale up and scale down of compute and network and memory, which is a big thing. So we can actually scale up the database cache at runtime, and then we can scale it back down without a restart as workloads come and go. And so, we need to be able to scale down as much as we scale up and have customers pay for what they use. All right. So then we have customer level scale. So for individual customers, some of them run thousands of Aurora clusters. I mentioned Amazon fulfillment. All the packages shipped by Amazon come through Aurora clusters. That team has thousands of them. And so how do we build the right customer experience for customers that are running thousands of clusters, thousands of databases? We have a lot of SaaS providers that we work with. They host their own multi-tenant applications and run on Aurora, and they may have millions of customers. And so how do we build a system that's easy for them to use? How do you build a system that lets, say, a cloud software provider make sure that they have the ability to scale individual customers up and down and their resources? And then we have service level scale. How do we deal with managing all those thousands of systems that Murley talked about, the storage systems? How do we manage the health of those, the heat of that? How do we let customers self-service because we have so many customers? So those are some of the challenges we have at scale. Next slide. And I'll try to wrap up here. I think it's probably the last slide. Then there's other really cool things that we have because we're in AWS. So we can work and partner with the EC2 hardware networking teams. So we always want to ask ourselves like 3 questions. Are we leveraging what EC2 is putting out? Are we prepared to leverage what's upcoming from EC2 and networking at AWS? And then what can we ask them to build for us? Can we ask them to build custom hardware for Aurora? I mean, we can ask them, but what do we want to ask them to build? What's the ideal hardware for such a system? Are there different types of SSD, NVMe drives that we want? Are there different ratios in hardware to in CPU and memory to network that we want to tweak? How do we want to place the network? These are all things that we can work on, and then we do discuss with them to make Aurora a better service for our customers. And then there's the rest of the AWS ecosystem. We have some ML integrations today. You can call serverless Lambda functions via SQL. We need to do better, and on our federations is we have data sources. So there's opportunities there, right? So there's a lot of stuff that can be done within the AWS ecosystem that's there for Aurora still. Okay, I think that was the last one. Yeah, all right. So we've got 2 publications if you want to go do some reading that were published at Sigmod that go through some of the background of the Aurora system. So I went a little over time. I thank you all for joining and listening to us. And I believe right now I'll throw it back to Max